for this subject, right? So this is kind of past paper. The one that we had in October 2021, right? So I'm going to discuss this paper because it's the latest paper that I have for you related to your module, right? So basically, in our discussion, we had we basically had some sections, some important sections, right? For example, we had a discussion on the history, the evolution, and the expectations of intelligent systems. That was one major section that we did. So that was a kind of a, from a philosophically as well as technically, how this field of study began and how it was evolved and what were the expectations and probably what is the scope, right, of this particular subject. Then we discussed some applications, right, the critical applications of artificial intelligence as of now. So that we did. And also we discussed about the concept of intelligent agents, right? Concept of intelligent agents. And then we move to one of the most important things in artificial intelligence, or one of the most important things that we try to accomplish through artificial intelligence, that is search, right? And search is actually a universal problem, right? When solving problems, we need to search. So search is one of the most important things that we try to do using artificial intelligence. So we discussed about search. And when we discuss about search, we discussed about informed search and uninformed search. And we started with uninformed search, or what we call blind search, or exhaustive search, or brute force search. So those terms are more or less same. And so we basically talk about uninformed search. Then we realize that uninformed search is a waste of resources and it consumes our time, effort, energy, and space in our computational resources. So we need better algorithms that can make use of available information to make a better decision. So we discussed about informed search or heuristic search. From heuristic search, we move to meta-heuristic search techniques like genetic algorithms. And we basically discussed about the concept of optimization as well, right? Then we, based on that ideas, right, we move to another important area called machine learning. Because when we discuss about the history and evolution of artificial intelligence, we learn that there are two basic pathways of AI. One is the rule-based pathway, and the other one is the data-driven pathway, the connectionist pathway. So in that data-driven pathway, we realize that machine learning has emerged, right? Has emerged a lot, and it is continuously being developed. And therefore, machine learning is a very important area in artificial intelligence. So we discussed the basics of machine learning, what is meant by machine learning, how machine learning happens with the help of data, the supervised learning and unsupervised learning. So we will be having a deeper discussion, or maybe a better discussion when we talk about machine learning in the next trimester. I don't know with whom, maybe me, but or maybe with someone else. You'll be discussing about machine learning in detail. But I gave a general introduction to machine learning, right? What do you mean by training machines with the help of data to make some decisions? There we learned about predictions of classes, and also predictions of numbers. And then we move to artificial neural networks, right? So as one of the major fields of study in modern artificial intelligence, and also as a major technique that we can use to do machine learning. You learn the basics of artificial neural networks. So there you learn the fundamental unit of that learning process. That neural network process is as the neuron, the biological neuron, the architecture of the biological neuron, and how that biological neuron architecture has been modeled as a computational unit, right? And how the components of the biological neuron have been mimicked, or let's say have been implemented as a mathematical model in the computational model of the neuron. And then we discussed about some basics of that artificial neuron, the basic ideas of that artificial neuron, then the basic functionality. And then we moved to the concept of neural networks, right? And neural network learning, how neural networks learn, right? And the concept of backpropagation, right? The most important, or rather, one of the mostly used learning algorithms in neural networks called backpropagation. So we learned about backpropagation algorithm as well. Then we move to, from there we move to the other branch of artificial intelligence. There we basically discussed about rule-based systems, right? How rule-based systems are implemented and how rule-based systems work, right? And I introduced you the concept of if-then kind of rules, right? So how a particular condition can result a particular action, right? So that kind of a discussion we did. Then we move to, from that we move to fuzzy logic, because the traditional rule-based systems works mainly with binary logic. In the binary logic, there can be only two states. One is true, the other one is false. So your if-then kind of rules also can have their if part implemented using binary logic, right? So that if part can be either true or false. The then part is also either true or false, right? But in our natural human decision-making process, we don't work with that binary logic very much, right? We always talk about, we have some fuzziness when we talk, right? For example, if the temperature is low, if the temperature is medium, if the temperature is high. So how much high, how much medium, how much low, that's always vague, right? It is vague. So there's a big vagueness in that way of talking and thinking of humans, right? So we always use that sort of vague linguistic terms when we make discussions and also when we make decisions. So fuzzy logic is a mathematical system, a logical system that is similar to the binary logic, and the fuzzy logic system helps us to implement fuzzy rules. So with the help of something called membership functions. So we discussed about those fuzzy rules, fuzzy logic systems as well. So I introduced you how control systems, right? Control systems work with the help of fuzzy logic, right? A control system is any system that kind of control a particular process, right? So controlling the cooling process in an air conditioner. So air conditioner could be considered as a control system then, right? According to the information that it gets from the environment. It makes a process and it processes that information and then controls the temperature of the room by changing the speed of the blower motor, right? So basically, the idea is something like that. So that control process is happening inside the air conditioner. So air conditioner contains a control system, right? The water valve, opening and closing of a water valve, water supply process to be considered as a control system, right? You may, based on the usage and the supply of water, the tank can, the valve can automatically adjust the input or the inlet to the tank, right? So the water inlet and the water outlet. So based on the consumption from the outlet, can control the inlet valve. So there is again a control system, right? If you have a watering system to some plants, and if that watering system needs to be controlled using some intelligence or rather in an intelligent manner, that can be considered as a intelligent control system. If there's no such intelligence, it's just a timer-based watering system, then it's just a control system. So to make those control systems more intelligent, you can make use of concepts like fuzzy logic. Or rather, you can basically use the techniques of artificial intelligence, and fuzzy logic is a good candidate solution for that. So it's like that, right? So those were the things that we discussed in this class, right? So that explanation that I did so far during the past 15 minutes or so, that is basically what we discussed during this course module. So when you are studying, now based on that explanation I did, you can decide what to study and what not to study. So basically, if you look at this paper, the duration of the paper is 2 hours and the number of questions is 4, right? So let me explain. I have not decided yet the structure of the paper that I'm going to give you. I had a request to get a 3-hour paper and 5 questions and maybe 6 questions with some choices and so on and so forth. I have not decided yet, but I personally I prefer giving answer all kind of questions rather than giving options, because I did not cover much during this module. What I did was I tried to be as simple as possible to give you the concept of intelligence rather than trying to cover as many techniques as possible. So because what I thought was, if you can understand what these intelligent systems are, then the new techniques can be added to that as and when you get the requirement. Otherwise, what is required is for you to have the idea that the computers can be made intelligent. They have been made intelligent to some extent, and what are the limitations that they have and what are the expectations on that, right? So if you have that basic understanding, if you, let's say, if you try to go and implement it somewhere in your workplaces, then that implementation would be more successful, because you know what sort of things that the computers can do, and you can even search what are the things that they are at the moment accomplishing in different other workplaces, right? So then you can become a kind of leader in absorbing intelligence and intelligent systems into your respective workplaces. So that was my intention. So if you are a teacher, for example, then again you can give that basic idea of intelligence to your students when you talk about AI in the IT curriculum. Then you have that basic understanding, right? So what human intelligence is, what animal intelligence is, and how this concept of intelligence be implemented in a computer. And when you do so, what are your major expectations and what are the practical possibilities? Or rather, what is the practical limit that you can implement that intelligence into a computer. So that was my intention. So I believe that there's nothing much to give different options for you, rather than trying to see whether you have understood that particular domain properly. So let me take you through these questions. Explain with reasons why you agree or disagree with the following systems, right? Explain with reasons. So you just can't say you agree or disagree, but you have to provide some reasons as well. So these kind of questions, actually, I can extend even, right? So here you have only 5 things. Actually, this was conducted as an online exam. This was not a physical exam because in the last year, October, this was October, yeah. Last year, October, I think we had some issues related to COVID. So I made it an online exam, and because of that, I limited this to 2 hours. So perhaps I can extend these questions and make them bigger and add more content into this paper and make it, let's say, 2.5 maximum, right? And maybe I can increase the number of questions also, so that you can have only 20 marks, for example. So basically 5 questions, 2.5 hours, or 5 questions, 3 hours max would be the general structure of the paper as I'm thinking now. So let's, the Turing test is well suited to test the intelligence of a machine. So this kind of a statement requires you to have an understanding what Turing test is. Right, so you know that Turing test is a test proposed by Alan Turing in 1952, right? So at the time, even the term artificial intelligence was not coined. It was coined in 1956. So when the scientists study about making machines more intelligent, so they had different thoughts like this, right? So how do we know that a particular machine is intelligent, right? So these are, like, when you look back now, you see, you might think that these are simple, but that is how this field progressed, right? So when it grew, people got this requirement. So how am I going to say that a machine is intelligent? How do I know that I have built an intelligent machine? So these are kind of standards that you require. So Turing proposed a test called Turing test. And what Turing said was, I think you have to go and see, right, what Turing test is. So Turing said, if a human interrogator passes a question through a screen to someone or something behind that screen, which the human interrogator can't see, right? In text format, you pass a question through a screen to the other side of the screen. From the other side, you get an answer to that question, right? The human interrogator can't distinguish whether that answer came from a machine or a human. Actually, behind that screen, there is a machine, right? So unknowingly, the human interrogator sends that question through the screen to a machine, actually. Machine provides the answer to the human interrogator, and the human interrogator cannot distinguish that it came from a machine or a human. If so, that machine behind the screen is intelligent. That is what Turing said. Now it is like you are chatting with a chatbot. Now, if you go to Facebook pages of many businesses, or even you go to the Facebook page of some reputed companies, you happen to interact. They have provided you a sort of chatbot, right? Now you can see how intelligent those chatbots are. So actually, according to current research, chatbots, and that is also part of robotic process automation. So this technical support or the call center work can be automated with the help of AI. And when you do that, you call it robotic process automation. Robotic process automation. So process is automated using robotics. So one way of doing that is providing a chatbot. So when you're interacting with the chatbot, you are submitting your question in the form of text. And the chatbot provides you an answer. Right? So if you cannot distinguish that the answer came from intelligent algorithm, right? From an algorithm, it's an algorithm, then you can say that that particular algorithm is intelligent. Right? Now you can recall your experience with some some chatbots, and can try to convince yourself whether they are intelligent or not. Right? So the question here is, the Turing test is well suited to test the intelligence of a machine. So is it suited as of now? Right? Now you need an opinion in this case. Right? So are the machines that we talk about, are the intelligent systems that we conceptualize these days, only having these text interfaces? What are their speech interfaces that you have? For example, you do verbal communication, right, with some systems. So it's not text-based now, it's verbal. And those machines are now moving like humanoid, right? Humanoid robots are there, like you saw Asimo. Right? So can Asimo's intelligence be tested using only a text Q&A method? Right? So your opinion about this was what I expected. So even though you have 5 questions here, now you can see there is an opinion for you to say. Right? So that opinion must reflect that you have a deep understanding about this subject. Okay, so there's the answer to that question I expected was that you have to have a bigger understanding beyond the Turing test about the concept of intelligence and the limitations of this. So if, let's say, using all possible methods that you usually interact with a human, right? If you interact with the machine behind that screen, if you let that user to interact with the machine behind the screen, and if the user still cannot figure out whether that answer or whether that response came from a machine, then of course you can say the machine is intelligent. But Turing test was the scope was limited to text-based Q&A interaction. And the second question is, so I did not give an answer, right? So you must now, when you are studying, you must try to formulate your answers to that question. So an intelligent agent is always rational. So we discuss this concept of rationality. As human beings, we always like to make our decisions as rationally as possible. Rationally means like sensibly, right? So you must justify. You have to have a strong justification about the action you took. Right? This is why I thought so. This is why I decided that way. This is why I say that it's going to happen this way. So rationality. Right? So an intelligent agent is always rational. So this is a question because of uncertainty. Right? You can be rational. You can be 100% rational if you have enough information. Right? If you have enough information, can be 100% rational. What do you mean by enough information? If you have enough information, let's say full access to information, right? Full access to information, there's nothing called uncertainty, right? There's no uncertainty because they are certain. If you take the environment that the agent is in, like you say, you are in this physical environment, your surrounding and your environment. Tomorrow you go to work, let's say, then you are in your work environment. That is again, you have an environment, right? So the environment around you on which you act. Do you have perfect information about your environment? No, right? Because there are limitations. Your senses are limited and certain things are uncertain. You have other processes taking place which are stochastic, and because of that, your environment is changing rapidly, right? So, and it's now something, next time it can be something else, and you can't predict all the things. You can't get perfect information about all the processes that contributes to the change of the environment. So how can you make a rational decision? Because you don't get perfect information about your environment. You can't observe your environment fully. We call it partial observability. You have only a partial observability on your environment. So when you have a partial observability on your environment only, how can you be rational? So your rationality, right? Your rationality as a human agent is bounded by the limitations in the observability of the environment. Same thing is applied to intelligent artificial agents as well. I have not said artificial agent here, but even in the case of artificial agents, you have that limitation. Because the artificial agents have some sensors and actuators. There are limitations of those sensors and actuators. So they can observe the environment only through the sensors that are designed in those artificial agents, right? So sensors only allows them to take percepts from the environment. So their knowledge about the environment is always bounded by the sensory information that they get through their sensors. So those limitations always limits their rationality as well. So we can't say that intelligent agent is always rational, but they try to be rational, but their rationality is bounded by the limitations of information about the environment. Third one, if you have any questions, you drop a chat message, right? Modern intelligent systems are use hybrid techniques. Again, you need some understanding about the modern intelligent system. What is this hybrid technique, right? Hybridization. Now, we learned a few fundamental techniques. For example, genetic algorithm, neural net, fuzzy logic, brute force search, heuristic search, right? So we learned those things. What do you mean by hybridization? Those are techniques, right? So what we learned were techniques. So there are other techniques as well. So intelligent techniques are there. Reinforcement learning could be there. So there are also techniques, right? Now, what do you mean by hybridization? Hybridization means you combine those techniques to make the system better intelligent or more intelligent. You combine those techniques, hybridization. For example, can you improve the neural network using fuzzy logic, right? Can you improve the learning process in a neural network using fuzzy logic? Or else, one of the major limitations that we learned in neural networks was the reasoning ability. So neural networks are like black boxes. Given a question, they provide you the answer. But if you ask why, what is the reason? Right now, if you say something like, as a human being, if you say something, let's say, it's going to rain tomorrow, right? I ask you why. You can give me some kind of reason, right? Maybe it could be acceptable or not acceptable to me. That's a different story. But your reasoning is communicable, right, to me. Right? You can communicate the reason for your prediction. You said tomorrow it's going to rain tomorrow. You can tell me why you thought so. But neural networks, they can tell me whether it's going to rain tomorrow or not. To some large extent of accuracy, they can tell me as of now. But it can't say why it came to that conclusion. It is difficult, right? So that is a limitation. So can we combine neural network with some other technique to overcome that limitation? Right? So hybridization. So modern intelligent systems actually use hybridization techniques. Right? For example, there's something called fuzzy reinforcement learning. So reinforcement learning combined with fuzzy logic. Fuzzy neural networks. Neural networks combined with fuzzy logic. Right? Neural networks can be combined with genetic algorithms. Because in neural network learning, there's an optimization. You have to minimize your error. And you have to find out the optimal set of weights, right? Optimal set of weights that minimizes the error according to the input data set, right? That is what you call neural network learning. So for that, right, backpropagation is the algorithm that we have proposed. Can we use can we use genetic algorithms? Can we use, let's say, swarm intelligence, right? We have not discussed swarm intelligence, but I think I gave few thoughts about swarm intelligence as well. Let me talk about beehives and all. So that is what we call hybridization. So modern intelligence systems use hybrid techniques, right? The robot called Asimo is intelligent. Again, you have to understand what Asimo is. I showed you Asimo. So if I have shown something in the class, then that can be asked, right, as an example. So Asimo, you saw Asimo, and you have to have an opinion whether the robot called Asimo is intelligent or not, right? Now you have to have a broader understanding about intelligence and intelligent abilities, right? What are the usual intelligent abilities that we have as human beings, right? So we can perceive information from the environment and we can remember it, right? We have to have a memory. We can remember. We can synthesize information, right? We can make predictions. We can communicate our decision to someone else. We can interact with someone. Right? We can verbally communicate. We can, using gestures, we can communicate. We can get the communication from the others to us, right? So inward communication, outward communication, right? And we can do logical reasoning. And not only that, we can walk, for example, right? So those kind of moving abilities are there, right? So many intelligent processes are taking place. So we can make decisions according to the environment, right? So we can act on the environment in a sensible manner, and we can handle equipments, right? So those kind of things also can be considered as parts of the intelligence. So, but at the same time, we as human beings, we can think. Right? We can think. So we can think and act. At the same time, we can learn new things. Right? I can learn to drive a car, for example. At the same time, I can learn to swim. And I can learn to play golf, for example. Right? So various things I can do. I can learn to play a guitar. I can solve mathematical puzzles. I can solve mathematical equations. I can design certain systems. Right? I can resolve conflicts sometimes to some extent. Right? I can resolve conflicts with someone. So those are my abilities, right? So my different and my diverse set of abilities and my diverse range of skills and my diverse areas of application of my skills. Now, with that explanation, you can see whether Asimo is intelligent. Now, you have to make use of terms like artificial general intelligence, artificial super intelligence, artificial narrow intelligence, right? Those three. Or weak versus strong AI, right? What is weak AI? What is strong AI? Strong AI means actually the robot is thinking, right? The thought process is happening inside that system. In narrow AI, the robot is not actually thinking, but it pretends to be thinking. It only pretends to be thinking. So this argument came up from the Chinese room argument by George Shelley. Right? Chinese room argument was developed as a criticism to the Turing test, right? The effectiveness of Turing test. So what Shelley said was, even though Alan Turing says that using that his famous test, you can test an intelligence of machine, even a machine which is capable to process large information, theoretically, which does not have a thought process, but only have a function, right? Only have a function which is able to process information. that can still pass the Turing test without an issue. You can search for the Chinese room argument on the internet, on YouTube, for example, watch what it is. And according to that, according to John Shirley, a machine can pass the Turing test even if it is not actually thinking, right? Because by just pretending that it is thinking, right? If it has a fast information processing capability. So with that understanding, you must provide an answer to this question called a robot called Asimov is intelligent. So actually, you might understand that the general idea here is that Asimov is not intelligent compared to the human beings, right? So it exhibits only narrow intelligence. Heuristic search is better than exhaustive search. Now you must remember what heuristic search is, right? Heuristic search, before that you have to remember what exhaustive search is. Exhaustive means exhausted, right? So you are exhausted. What do you mean by that? You are tired, right? You are, right? So if someone has put the answer exhaustive equal blind, yeah. So you are exhausted because you are blind, right? You are aimless. You don't have any guidance. So you try to search something, but when you try to search it, you are just wasting your resources. Now, for example, as I usually take in the class, I usually forget where I drop my key, right? In my home, right? So when I return, I usually drop my car key somewhere. Can't remember, right? Next day morning, I can't remember, right? So it's something that happens very often. Now, if I just search without any information on the following day, I'll be just wasting my resources, right? I'll run here and there looking for my key. It also happens, right? So I get tired because I am blind. I don't make use of the available information. So I'm tired. I'm tired of running here and there looking for my key. Exhausted. I am blind because I'm not making use of the available information, or I don't have that information available with me. Right? So it's exhaustive search. Heuristic means then use some information available, right? From my practice over the past, I know that these are the places I usually keep it. It's a kind of heuristic information I have, right? What is the door that I usually use to get into my home? Is it the front door or the rear door? Right? And are there any specific places where I usually go when I reach home? Heuristic information. Because if those are the common places that I normally go when I return home, and those could be the places that I dropped my key at, right? That is usually happen. So that is how my search is driven usually, right? So I'm making use of those kind of heuristics that I have learned over the past, right? So they're not concrete information, they're not concrete facts. Rather, they are just some helpful information that I can make use of. Again, for example, I can ask my mother, where did I go yesterday evening? So she usually remembers, right? So heuristics, right? So I can make use of that information. So my example to you was like, if you are going to return home, return to University of California on a Friday evening from Bambalapitiya to the University of California, are you going to be, when you are selecting your route, right? Let's say bus route, or maybe you are driving a car, then what is the route that you must take, right? So are you just blindly taking the shortest route according to the distance, or are you going to make use of some available information that you have? You're based on your previous experience, or based on the news that were on media, like the protests taking place at the Fort railway station, or the Lipton roundabout, right? Or else what your friends have told you about the traffic in Colombo City. So you are going to make use of that, right? So make use of that information, and you are considering the time of the day, and you are trying to synthesize that information that you have received to decide which path, even though it could be far, considering the number of kilometers, still you can complete your journey within limitless amount of time if you make use of that heuristic information. So heuristic search is always better than exhaustive search because heuristic search make use of the heuristics or the available information that guides you towards the solution that you are looking for, right? Search is basically trying to give you three things. One is a solution to the problem, or all available solutions to the problem, right? You are searching for a solution or all available solutions. The third thing is it can give you the optimal solution or the best solution. So you are not only searching for a solution or many solutions, you are searching for the best solution out of many solutions. Right, so heuristic search is better than exhaustive search. That's true. You have to explain this with that kind of facts. So what I have noticed in students' answers is that you're not capable of, not you, right, the students generally, with those who are about whom I have experience, right? They're not capable of building up an effective answer. You just write something, right? You just write something, but you just don't build a logical answer with proper reason. So that makes it difficult for me to assess, right? So usually you get less marks to these kind of questions because of that inability or ignorance of the need to provide a logically sound answer that reflects that you have truly learned this subject. So just for the sake of passing, sometimes I have given marks, right? But that is not right. So if I fail you, then of course, I think, I mean, you should not fail this subject, right? So make sure that you learn logical, to provide logical answers. Right? Remember also you have to take 50 marks to this question. You have submitted me some assignments as well, but still, you have to put some effort to pass this exam paper as well. The second question is about artificial intelligence. Third question is about state space tree and the search techniques and the genetic algorithm process. Fourth question is about fuzzy logic systems, right? So let me take you to the second question, or rather, shall we take third question first because it's about search. Draw a state space tree for the Tower of Hanoi problem. Make your diagram as self-explanatory as possible. Now, we discussed this actually in the class, right? So this state space tree for the Tower of Hanoi problem, we discussed in the class. I also introduced you a couple of other problems as well, problems like this, right? The Tower of Hanoi problem is a search problem because you are finding a way or ways to take those set of disks from one peg to the other peg, making use of the third peg as well, adhering to some rules. What are those rules? You can move only one disk at a time. You can't place a bigger disk on a smaller disk. Those are the rules. So without doing that, how can you do that placement? That is the problem, right? So when you're trying to solve that problem, then you must draw a state space. First, you have to understand what a state is, right? State representation. What is a state? What is the current state? What is the state that you desire? And what are the intermediate states? So currently all disks are on peg 1. The desired state is you want all disks are placed on the peg 3. Now, when I'm explaining this, I expect you to have studied. So if you have not studied and if you have just come to the revision class expecting to study something, well, that is not going to happen. If you have studied something only, this session is going to be effective. So now you have that start state and the desired state. Now you have to have that ability to conceptualize that state in a mathematical form, state representation, right? How can you computation or mathematically, if you represent it mathematically, then of course it becomes computational because it can be implemented inside a computer. So how do you conceptualize that state? How do you represent that state in a mathematical form so that you can convert that into a computational process? So Tower of Hanoi, we discussed how a state could be represented and what is called the state space. State space is the search space. That is the space on which you perform a search. So if you have a state representation, what are the all possible states that this particular system can have? Right? That is what you call the state space. So from the state, you can define the state space. To define the state space, you can make use of two ways, two things. One is a tree. So state space tree. State space can be represented in the form of a tree. Right? That is what you learned when we discussed about the water jug problem. You learned how a tree can be implemented. When you discuss Tower of Hanoi, we learned how to make use of a tree to represent the state space. When we discuss about the missionaries and cannibals problem, we learned how to represent the state as well as the state space in the form of a tree. When you learned about the uniform cost search, where the objective was to find the shortest distance between one city to the other or one node to the other to another, again you represented the state in the form of a represented the state as a single element state, like city, for example. If you look at if you want to find out the shortest distance between between two cities, right? And out of many cities, so each city is going to be a state, right? So currently the agent is in city A. So currently the agent is in the state A. The agent is desiring to go to state G. So it is desiring to be at state G. So from state A to state G, what are the other intermediate states? Right? Again, it's a different state representation. Right? Now, in that case, again, a state space has to be represented. The state is a city, for example, and there are many cities. What is your state space then? Your state space could be represented not as a tree this time, it can be represented as a graph, right? Graph. So if you remember that video about uniform cost search, that video explains a graph, right? So that graph helps you to perform a search. So uniform cost search algorithm is designed to work on a graph. We also discussed about traveling salesman problem. In traveling salesman problem, we did not have intermediate states. Our state representation was that we take the complete state in the sense each solution. Now, for the traveling salesman problem, remember, let me take for this one, let me take a okay. So in the traveling salesman problem, so in water jug problem, for example, from 0, 0, right, to we can move to either 0, 2 or 0, 4 or 3, 0, right? From 0, 4, then you can move to some other states, and finally you must reach the goal state of either 0, 2 or 2, 0, right? So you must reach these two. So this is the goal state, this is the start state, these are intermediate states. In the case of in the case of shortest path algorithms like uniform cost search algorithm, so you have some cities from A to B, B to C, and C to G, and from B you can move to D, and from there you can move to E and then come back to G. From A you can move to let's say move to F, right? From F you can move to D and then to G, right? So there's a city network like this. So this is a graph. So on this graph, you can find out different ways of reaching this. You can reach what is the shortest path of reaching G. It's a different kind of problem. Now here, the state is this one, right? This is a state. This is another state. This is another state. So if there's an agent, the agent can be at this state or this state or this state or this state. This is the goal state and this is the start state. Here, okay. This is a kind of multiple locations, right? So the state representation contains multiple locations, whereas in this case, the state has only one location, right? Like atomic representation. There is another problem that we learned called traveling salesman problem. In the traveling salesman problem, you have multiple cities, city, right? Now each city is connected with all other cities, and our objective is to start from A, complete a full cycle of a journey. That means visit all cities and return back to this city, right? Then what is the shortest cycle that we can make use of? What is the shortest cycle to start from A and return to A after visiting all other cities? To find the answer to this, right, we can represent this is the graph representation of the state space, and we can also have a tree representation from A to B, A to C, A to D. From A to B, you can move to C or D. From C, you can move to B or D. From D, you can move to B or C. From C, you can move to D and back to A. From D, you can move to C and back to A. From B, you can move to D and back to A. From D, you can move to B and back to A. From B, you can move to C and back to A. From C, you can move to B and back to A. Right? So A, B, C, D, A, D, C, B, A. So these two are like clockwise and anti-clockwise paths, right? So you can assume that it is same, or it can be different as well. So, for example, in the morning, if you go to Colombo side, it takes more time than coming from Colombo to your destination, right? So cost-wise, you can't say that it is always same, the clockwise and anti-clockwise, right? So you can consider them as two different paths. Now, what I wanted to say was, now this is the same state space, right? But this is tree representation, and this is the graph representation. So what we can solve this problem in different ways, right? But one way is considering kind of each solution as a state, right? Because you have a large number of states in this problem, right? So you probably now understand that it has large, I have shown you, right? So when the number of cities increase, the number of possible paths is increasing exponentially. So you take each path as a state. So it also has to be represented as a multi-location state representation. But in this case, that state representation is a full configuration of an answer, right? Each of this state, each of this branch is a solution, right? This is a solution, this is also a solution, this is also a solution. So out of many solutions, you are finding out the best solution. So each solution is a state. In this case, intermediate states are not solutions. In this case, they are solutions, right? So depending on the problem, right? So you have to decide what is a state, what is a state representation. Okay. Something wrong with this. Right. Let me get back to the question paper. Okay, so draw a state space tree. Now this is just an example question. So you must understand that what you must have studied, right? The concept of state space, right? This must be well understood, right? So we have discussed a few problems in the class, right? I think I did not discuss, but I introduced you the concept of Tower of Hanoi, N queens problem as well. In my slide set, you have that N queen problem, right? So N queen problem means what? On a chessboard, right? Chessboard, a usual chessboard is 8 by 8, right? I think it's 8 by 8. 8 by 8, right? So let's say it's 8 by 8, right? So 8 by 8. So let's simplify it to be 4 by 4, right? So if it is 4 by 4 board, it's like this, right? Usually in the game of chess, the queen, right? Queen can move vertically, horizontally, and diagonally, right? So if you have a 4 by 4 board, and if you have 4 queens, there are no 4 queens, but let's say we have 4 queens, right? We want to place these 4 queens on this board. Okay, this is not chess, right? Not chess, but we are taking some rules from the chess and this queen, concept of queen, and the movement, the possibilities of movements for queen. And we are trying to place those queens on this 4 by 4 board. If it is an 8 by 8 board, then we have 8 queens. So n queens means if there's an n by n board, if there's n by n board, we have n queens, right? So here it's a 4 by 4 board and we have 4 queens. Can we place these 4 queens on this board, right? Without letting each queen to cancel out each other, right? For example, I place the first queen here. Then if I place my second queen, I can't place the second queen here because diagonally each queen can cancel out the other. We can't place the second queen here either because vertically the 2 queens can move and cancel out each other. When I say each other, whoever moves first. I can place my second queen here, right? Third queen, where can I place my third queen? I can't place the third queen here because this queen can cancel out. I can't place my in this square because this queen can cancel out. Can't place here, this queen can cancel out. Can't place here, this queen can cancel out. So is there a way for me to place these 4 queens on this board? Another problem solution situation, right? So I don't know whether there's a solution existing for this problem. And there can be not only one solution, there can be multiple solutions as well. So how can I find it out? Right? Now, for example, if I don't place it here and I place it here, then where can I place my second queen? Here? No. Here? No. Here? No. I can place my second queen here. Right? Third queen, can I place my third queen here? Apparently, yes, right? So if I place my third queen here, this queen cannot cancel out that. This queen also cannot cancel it out. Right? So I can place my third queen here. Fourth queen, can I place here? No. Can I place here? No. Can I place here? This queen's access is only to this one and this one. This queen has access only to this line, and diagonally to this line. This queen can have access to these lines, this line, this line. So I can place my fourth queen here, right? So this is an answer. This was my intuition and my trial and error, and now since I have studied this for some time, I know that this arrangement is there. But for you who is hearing this about this problem for the first time, you can't find it out, right? And if it is an 8 by 8 board with 8 queens, now the complexity increases. If it is 12 by 12, for example, then again it increases, right? The complexity increases. So how can we find out answers to these kind of problems, right? So again, state space. So what is the representation of a state? Okay. So try to understand that concept of state and the state representation. So that's the idea that I have to communicate from this question, right? So this is just an example question, but you can get similar questions. What is the difference between uniform cost search and A-star search? Now you must remember that uniform cost search and A-star search are more or less same. They are all, both of them are shortest path problems or shortest path algorithms, not problem, shortest path algorithms, right? Both of them help us to find the shortest path between two nodes in a set of nodes connected to each other. What is the difference? What is the difference between uniform cost search and A-star search? A-star is a heuristic search algorithm, whereas the uniform cost search is a blind search algorithm or exhaustive search algorithm. Many students had forgotten this. Right? Many had forgotten. Right? So try to remember that the concept of uniform cost search and the concept of A-star search. I have given videos in my slides to both. Watch those videos, right? And you must have a thorough understanding about the concept, right? Concept of heuristic search, concept of blind search, and these algorithms as examples to each of that technique, each of that approach. Okay, so A-star is a uniform cost, A-star is a heuristic search algorithm. It makes use of a heuristic function. Not only the distance function, it has a heuristic function that together it makes the cost function. Right, so that's mathematical explanation, but the A-star search makes use of some heuristic information, not only the total distance that you have traveled so far, but also it makes use of some heuristic information that tells you some additional cost of being at a particular state. So with that help, you can decide where to move from here onwards. A-star search is that. Whereas uniform cost search makes use of purely the information that you have traveled so far, right? The distance that you have traveled so far. So try to differentiate the two based on that explanation. Do you think hill climbing search is a good approach to solve optimization problems? Justify your answer. Hill climbing falls into the category of local search, right? Local search. So you have, you are at a particular state, right? You're at a particular state, and the goodness of that state, we discussed that, right? I finally gave the word called utility, right? What is the goodness of being at a particular state? That is used in this kind of search techniques, right? So each state is associated with a goodness or fitness value, right? Fitness value or utility value, right? So basically the idea is, how happy are you when you are at that particular state, right? You were at a particular state before you registered to this master's course, but you wanted a better utility. You thought, okay, by doing a master program or getting a master's degree, I will be happier. Right? So once you are completed with your masters, you are at a different state, right? You are a master of IT, in addition to your other fields of studies that you have completed. So you are a master of IT as well. So you are at a different state. Educationally, you are at a different state. Maybe intellectually and, from a maturity perspective also, you are at a better state now. So are you happy then? Or will you be happy? You thought that you're going to be happy, but will you be actually happy? That depends. But you thought that, okay, by completing a master's, I get more avenues. I get more job opportunities. I can change my career, or I can migrate, or I can get more recognition. I can get promotion. That is how you thought, right? So each state is associated with some value, which is called a goodness, right? Or fitness or utility. It can come from a function. For example, you can define a utility function, or you can define a fitness function. You can define a goodness function, right? Both are all are same, right? So it tells you what is the likely happiness, likely goodness of being at that particular state. So what hill climbing does is, it allows you to move from the current state to a better state by changing some of the characteristics of your state, some of the elements of your state. So you change that element of the state and you move to a different state where you have a higher expected utility, right? It is like climbing uphill, right? Climbing up a mountain. Because you know that, okay, you have to, when you climb, your objective is to go to the top of the mountain, right? Top of the mountain, where you think that it is the best place for you to be at, right? So you try to climb up. When you are climbing up, you say, okay, if I take steps to this side, I'm going to be at a higher level than where I was. If I take a step to the other way around, then I'll be at a lowest place than where I was. So your objective is to go to the top of the mountain. So you always try to make steps towards the direction which increases your level eventually, right? So he'll climb. But then what is the, why is it a good approach to solve optimization problems? It is not. The reason is this. Probably as you remember, I have to, okay. Give me a minute. We have a process which is running. From process. Okay. And because of that, my slides are automatically advanced. Yeah. I think this one. Let's see. So a complex search space, right? A complex search space, like let's say in optimization, from optimization point of view, if your objective is to find the best solution out of many solutions, some complex search spaces, like if each state is if each solution is a state, and if you have multiple, a large amount of possible solution, then your state space is going to be something like this, right? So two-dimensionally, it's going to be something like this. To this side, these are the states, right? Mathematically, this is wrong, right? So this, from this x-axis, I have represented all possible states, every state. And to this side, I have the, let's say, utility, right? Utility or goodness, right? Goodness of the solution. Then I have multiple, let's say, depending on the current state. Let's say my current state is this one, right? I'm using the hill climbing approach. So I am climbing up this hill. I move from this state to this state. So this is state 1, and this is state 2, right? S2. This is 1, S2. From state 1 to state 2, I move, right? I make a move. Then my utility or my goodness is increased. Right? Similarly, I can move from each state to state, and I come to this point. Once you are here, then wherever you try to move, it is going to take you to a state which is lower than your previous state. Then you are going to stuck at this point because you don't take any further moves, because you think that this is the highest place, because you don't see other mountains, right? Because this solution space is very large, so you can't generate this entire state space at once. All what you can do is you can start at a random position, and then you try to locally advance your utility, right? Until you reach a point where no other step can take you to a higher state. That is what you can do. So your visibility is limited only to this, right? Your visibility, you don't see these things. So you think that you are here, you are at the top of the mountain, but actually you are not. You are at, there are even higher mountains around you, right? This is the ideal location, but you don't know about the existence of that location, at least. So this is the problem of hill climbing search. Depending on the place you start, for example, had you started from this location, then definitely, your hill climbing will take you to the best possible location. But that one cannot do that. So we call this, right? This is a local optima, right? And this is a global optima, right? So you can consider this as near global, right? Near global. It's kind of global optima is the optimal location, and this is like a near optimal location. But this is a local optima, and getting stuck at a local optima is kind of a issue, because it is not your best solution. You think that it is your best solution, but it is not the best solution. You can't find out the best solution, basically. So hill climbing is a local search which only allows you to search in the local vicinity. Doesn't allow you to see other completely different possibilities. It only allows you to explore your local vicinity, and it is called a local search, and that is going to take you to the problem of getting stuck at the local optimum. Therefore, my problem is solved. Therefore, the answer to that question is that it is not a good approach to solve optimization problem. Question is, if you use multiple agents, we can achieve a near global optima. Is that correct? Well, it is still not guaranteed. How many agents are you going to use, for example? Right? Multiple agents means how many agents? If I take that same graph, right? For example, I randomly choose 5 agents, right? Five agents. So one agent I place here randomly, right? So another agent I place here. Third agent is this one. Fourth agent here. Fifth agent here. Sixth agent here. Right? 6 agents. All use the local search, right? Hill climbing, or you come and stuck at here, come and stuck here, come and stuck here, come and stuck here, right? Come and stuck here, come and stuck, right? Now you might ask, you are the one who chose them, right? Why didn't you choose this location and this location? I deliberately did that, right? I did not choose those places. Just to show you that randomization still cannot guarantee that you are going to start at the mountain, right, at the top of the mountain where you have the highest peak. It is not guaranteed. It can happen, cannot happen. So a solution is not guaranteed, even if you do that. So local beam search, for example, right? In my slide set, you have that explanation. Local beam search. Local beam search basically is developed on this concept, right? Why not you start at multiple locations, right? But still, it is suffering from this problem that near optimal solution is not guaranteed even in that case. So that idea is it makes sense, but still it is not giving you the optimal solution or the ability to reach the optimal solution. So this is why we need global search techniques, some frameworks that allows you to, not only exploit a particular mountain, but also to explore the search space, explore the search space better, and then exploit eventually. So some frameworks. Those are called meta-heuristics. Now, why we call it a heuristic here? Goodness, right? Goodness is defined not by a concrete function, but by some available information, with the help of some available information. So that goodness is a heuristic, right? Expected utility, right? You are deciding to do a master's because you believe that it takes you to a different state, and at that state your happiness is higher, right? Expected utility. So that expected utility is what drives us towards the peak of the mountain, right? So that is the heuristic here. So that heuristic is defined based on some information. For example, you heard that from your friends that doing IT masters is going to give you a better job, right? So something that you have heard, right? Your perception. So based on that, your perception, what you have heard, and some information that you possess at the moment, you make decisions, right? So that is why we call it a heuristic. So that heuristic can take you to only to a local optimum. But if you can define a framework, a solution approach that can make use of those heuristics, but still it expands your search scope, not only to the local search, but also to kind of a global scope, that is going to be a better solution approach. So that is what we call meta-heuristic optimization. Local search is a heuristic technique. Simulated annealing is a local search technique, but genetic algorithm is a meta-heuristic search technique. It provides you a generalizable framework which you can make use of to find a near optimal solution, if not the optimal solution. So here I have a question from a genetic algorithm. Suppose a genetic algorithm adopts a chromosome structure given below, like this. Each gene can take a value V from vocabulary 0, 1. The fitness function Z is given as Z equal V1 plus V2 plus V3 plus V4, V5 plus V6. So it's a very simplified question, right? Only thing is you must understand what a chromosome is, what is a gene in the language of genetic algorithm, what is vocabulary in the language of genetic algorithm, what is a fitness function in the language of genetic algorithms. You have to have. Additionally, you have three functions let's say three functions or three processes, right? Usually a process is converted to a function in genetic algorithm literature. What are those? Selection, crossover, mutation, right? Selection means, now I assume that you know what genetic algorithm, the basic process of genetic algorithm, right? So evolution, the concept of evolution. So you have a pool of solutions. From that pool of solution, you generate some new solutions by combining the existing solutions, like the biological reproduction system generates new members of a species. So for the next generation, then we take a better set of individuals or solutions. Then based on that, you continue the process. You generate new individuals or solutions for the next generation. So when you pass through several generations, you believe that your individuals are better solutions to this problem. And those solutions could be near optimal as well, because it allows you not only to climb up a hill, but also to jump between hills, right? That jumping between hills is also allowed because you are combining solutions to make better solutions. So we learned about Holland's genetic algorithm, right? We learned about the selection process, roulette wheel selection and binary tournament selection. Don't forget these things, concepts, right? Then we learned about crossover, right? We learned about binary crossover. We have one crossover point and we take, let's say you have one chromosome and you separate, you divide that chromosome into two portions. This is your crossover point. You take this part separately and this part separately. You have another parent like that from where you can have two separate parts. Then you combine one part of the previous solution with the other part of the other solution, the remaining two parts of the solution. So you take two parents and create two children, right? So that is called crossover. Then mutation is it allows you to make a change to the value of a gene, a slight change to the chromosome, so that the solution is kind of different from the characteristics of father and mother. So let's say if you take you may have the features of your father, and also you may have some features of your mother. At the same time, you have features which neither your mother nor your father possess, right? So those features are coming from different other sources, and mutation helps you to have the difference from your father and mother. now this is the represent. Now this is very simplified, and it has been simplified in a way that it makes you understand the whole structure of the gene, right? Explain the, what is the question? So I'm taking a paper which is not moderated. So check whether I can take the moderated. Yeah. Question is this, right? So explain the functions selection, crossover, mutation using the above structure, right? Now, if you understand what is selection, what is crossover, what is mutation using the above structure, now you can explain, right? You have the object, you have the fitness function as well, right? So you can say how to make a selection, right? You can generate, the vocabulary is given. You can generate a few instances of solutions, and you can show what selection means, right? You can say, okay, this has a fitness of this has a fitness like this, right? So then if we create a pool of solutions like this, then they are going to be having different fitness values. Then selection using roulette wheels is going to happen like this, right? You don't have to explain both, right? You can say selection happens using roulette wheel selection. This is how it happens. Can say crossover, this is what we call crossover point, and if you select the crossover point like this is how two parents are going to give birth to two children. The mutation is this. So that's a very simple question that I have asked, just to see whether you understand these three functions and how to work with these three functions with the help of this fitness function. That is what I tested. But believe me again, right? Many people could not answer these questions. I maybe the way that they study, right? And because it was completely online, and they were sort of lost. This is question 2, and how comes question 3? We took the question 3. Right? Okay. So question 2 is the next thing. State 3 examples for the applications of artificial neural networks. This you must understand, right? So wherever it predicts a class, wherever it predicts a number, you can make use of neural networks, artificial neural networks. There's nothing called, don't send direct messages, send common messages to everyone. The question is, using meta-heuristic frameworks, how can find the global optima of hill climbing? So there's nothing called global optima of hill climbing, right? So we are searching for a global optima in a search space, in a solution space, right? So we have large number of possible solutions. In that large number of possible solution, we are finding the best solution. Only thing is, because of the partial observability, we don't see the entire search space or entire solution space. So hill climbing is, depending on the place you start, it helps you to climb up, and you're going to stuck at a local optima. You have the risk of getting stuck at a local optima. In a meta-heuristic approach, right? The meta-heuristic approach, like genetic algorithms, the advantage is that even though you start at this place, these respective places, let me take a different color for that. Right? So if you start at different such places, your path, your climbing up path is not only limited to this branch, right? Because you are not going to continue with this same set of solutions. You are going to combine this, and you are going to make new solution. For example, let's say you combine these two and you make a new solution, right? You combine these two solutions. Here there was a kind of cliff, right? So you combine these two solutions and you make a new solution here, right? So your new generation could be like including these places as well, right? So few from your new generation, right? So let's say after selection, your frontier is going to be like something like this, Okay, your frontier is something like this. These are removed. Okay, now you combine this in your, when you prepare the new generation, let's say your new set of solutions would be like this, right? Your new set of solutions, right? Then your frontier is going to be, now it's advanced, right? When you combine these ones, let's say you have these solutions, right? This set of solutions. This is your fourth generation. And you can see it is further advanced, right? So you started from this primitive set of solutions, and eventually they combined, and when you combine them, it is not the parent that you are continuing with, right? Not the same set of same path, right? So you are creating new solutions. So you are having a frontier which is always better than the previous frontier. So eventually we expect that you reach this, right? This may not work exactly this way, right? It's not guaranteed that you're going to get the global optimum, but some kind of guarantee is there that you're going to end up at a good enough solution, right? So that is how the meta-heuristic approach outperforms the heuristic search approach. So state 3 example for the application of artificial neural network. So automatic car, for example, right? Or a drone or something, right? So how can it move avoiding obstacles, right? Then you have to make classifications, right? You have to recognize the objects in the scene, and you have to classify, you have to classify it as having an obstacle or not, or you have to classify what that object is, and accordingly you have to have a strategy to avoid that obstacle and move forward. Predicting churning customers, predicting churning employees, predicting defaulters, predicting the price of a house, right? Predicting a disease, predicting weather, right? Whatever, predicting, right? Predicting the past, the outcome of an exam, right? Predicting the grade that you are going to get at an exam. Is it A, B, C, or D, right? So those things can be given as examples, but try to make them sensible examples. For example, predicting the house price and predicting the price of, let's say, fuel, right? And predicting the price of stock, they all look same, right? So predicting a price. Try to make it different examples, right? Try to present different examples. Then that difference is always going to be compensated in my way of evaluation. Briefly, have that understanding, right? So have some real applications, have an idea about real applications of these techniques that we study. Briefly describe the following components of Adeline architecture using a suitable diagram. What is Adeline? Now you have to understand what Adeline is. Adeline is a single neuron, right? Single neuron architecture. It is not a neural network. It's a single neuron architecture, right? In a single neuron architecture, basically the biological neuron is modeled as a computational unit, mathematically. So it must have inputs, right? So you must draw that diagram, right? So, you know, we took a standard diagram in artificial neurons. This is a neuron. To the neuron, through dendrites, you get input signals, right? So you have to have input signals to the neuron, right? And these input signals are connected with the neuron with some weight, some intensity values, right? So intensity means, like, when you take the percept, some percepts are stronger, some are less strong, right? So some percepts, it depends on the sensors that you have, the power of your sensors, and also the availability or the power of those signals in the environment, right? So some signals you hear strongly, some you hear less strongly, something like that, right? So intensity. And then you have an aggregation function inside this neuron called Z, right? According to the notation, right? So this, the actual thing does not have something called Z, but is a notation, right? Z is equal to W1 X1 plus W2 X2 plus W3 X3 plus W4 X, right? That is what you call Z. Then there's something called an activation function, G, right? So, and then you have the output Y, right? So Y is equal to G of Z, right? That means this Z is taken as the input to this path, the activation. The activation function takes Z as the input and it does a transformation and it produces this Y, right? Now, in the case of Adeline, actually, this aggregation function is a differentiable function. It's like usually in the perceptron, for example, you use the step function as the as the activation function. But in Adeline, you don't use the step function. You get the unit function or the identity function where, say, this X and Y. So Y equal X, for example, identity function. Or you can even use a sigmoid function like this, right? Or else it's 0.5, it's 0.5, 0, and this is 1. Okay. Sorry, made a mistake. So it's like this. Okay. You can use the sigmoid function, or you can even use the ReLU function. ReLU is something like this, right? As the function here, but not the step function. So you have that activation function, and then from the output of the activation function gives you a feedback mechanism, and that feedback mechanism goes back to the places of the weights and adjust the weights. Finally, when it gives you the output, right, the Y output can have another activation function where you have a sort of step function or something. Then it gives you the respective class. If it is 0, then one class. If it is 1, that's another. So in the training process, to change these weight values in Adelaide, you need to have a function which is not the step function, right? So let's go to question. Question says, describe the following components of the architecture: inputs, outputs, weights, aggregation function, and the activation function. So those additional things like how this learning and the feedback and those things, I have not expected you. I just have tried to find out whether you have studied these 5 things: input, output, weight, aggregation, activation. Right? But I told you that in the learning process, the weights are getting adjusted over and over, right? So once you expose the set of data to the neuron once, you get an idea about the overall error that it produced, right? We say feeding forward, right? When you feed forward through that neuron, right, those data, it produces outputs, and by comparing those outputs with the actual outputs, you can compute the error for every instance. And when you combine those errors, you get the overall error. Right? So that based on that overall error, you can make adjustment to this W values. Right? That those W values can be adjusted based on that error value. Right? Now, when you combine these neurons into a neural network, right? Neural network, you can see that weight adjustment is getting complex. That is where you need backpropagation algorithm. Right? So backpropagation algorithm helps you to adjust those weights according to the total error that the system produces at the end of each exposure of the data set to the system. I found a nice simulator. When I was explaining you this subject, I only introduced the SimBrain simulator. I don't know whether you checked that. There was a simulator called SimBrain. I said using SimBrain, you can simulate neural networks and understand how it works. But then when I was searching for something else, I found this simulator, TensorFlow Playground, right? TensorFlow Playground. If you go to this TensorFlow Playground, you can see it's like very simple, very browser-based environment for you to see how these neural networks function, right? Now here you have 4 types of input data, right? So input sets. As you can see, this is a very neat, all are binary classifications, right? And from here you can actually choose whether it is classification or regression, right? We have regression, classification both, but classification is very straightforward. So let me explain using classification. This has a very straight boundary, right, between the 2 data sets. Comparatively, this is complex because this has a non-linear boundary. As you can see, it's a circular boundary. This also has non-linear boundary, as you can see, right? So the boundary should be like this. So it's non-linear. And this is even more complex, right? The boundaries are even more complex. Now let's try to implement our neural network using this simulator, right? So how many hidden layers do I need? I can control from here, right? So I only need 1 hidden layer. Now here hidden layer means, in fact, these are inputs. These are not neurons. This is the output. And here only you have the neuron, right? So let's say we want a single neuron. So I reduce all the other neurons and I have only 1 neuron here. So this is like your adeline now, right? Like your adeline, only 1 neuron. And now we are going to classify this one, right? We're going to classify this using this single neuron. We have 2 inputs. We can define other inputs also, like other features like this, but I am taking only these 2 features, X1 and X2, straightforward, right? What is my activation function? I will use linear activation function like that identity function, right? So linear activation function I use, and I have a learning rate defined as 0.03. Regularization I don't want to set, and now I have created my architecture of the neuron, right? So I have 2 input values, and we don't know what the inputs are, but these inputs are corresponding to this actual data, right? So that we have to assume. Okay? The actual data set has these 2 classes, and we want to see whether this neuron learns a boundary, right? Learns a boundary that separates these 2, right? So this actual data. We want to have a boundary defined by this neuron to separate these, right? So I'm going to press this run button. Now you can see after 140 epochs, it has now separated the 2 classes very neatly, right? Very neatly it has separated. Now this is what we call linear separability. As you can see, the classification boundary is linear, right? Now using this linear straight line, now it has separated the 2 sets of items or 2 sets of data using this straight line. Okay. Now what I'm going to do is I'm going to take, let's say this one, right? This is a nonlinear boundary, right? As visually we can see that it's a nonlinear boundary. Can now a neuron learn that boundary? Let's see, right? So can this learn this boundary? If it learns this boundary like it learned in the previous case, it should separate these 2 classes using a circular boundary. Okay, let's see. I'm going to run it with the same configuration. I'm going to run this. Now it is learning, right? So here epochs means how many iterations that it is running. Okay. Now is it learning anything? Do you see any output? You can't, right? What is the reason? Because single neuron can only create a linear boundary. Can I change the function, right? And see. With ReLU, kind of a classification is taking place, but the misclassification is higher, right? See, this set of items are correctly classified. This blue set of items are also correctly classified. But how about these ones? They're not classified correctly, right? And let me try this one, right? You can change the activation functions also and see, right? Can it learn this pattern? Right? Let's run and see. Now this is the outcome of the neuron, right? Single neuron. So these ones are classified, but here you have lots of misclassification of this orange class, and also some misclassifications from the blue class. So it is not performing well. Quite understandable, right? So you can't separate these boundaries using a straight line. Very simple. Single neuron can only separate using a straight line. Shall we increase the number of neurons? So how many do you want? Let's say 3, right? Can we find out a boundary for this one? Let's say, right? For this one, can you find a boundary using 3 neurons? One straight line to this side, another straight line to this side, another to this side. Perhaps it can give us, right? Let's see. We're using ReLU activation function. Let's see. It's much better, right? So it gave us a kind of a, I don't know what it's called, right? So this kind of shape. A nice classification is built using ReLU. Can it do the same using linear activation function? It finds it difficult, apparently, using the linear activation function. Not very successful. Right? Even with this large number of epochs, still it is not performing well, right? Let's change the activation function to sigmoid, for example, right? Let's run sigmoid. Yeah. So it made, right? Made the classification. Just play with this, right? Just play with this and see whether you understand. Now, if you take something like this, okay, this one, for example, can it do that classification for this using sigmoid? It did, right? So eventually it learned the boundary, not very well, right? Not very well, but well with some higher percentage accuracy, it could, right? Let's change it to ReLU, for example, right? And run. It learned this part, but not this part, right? Struggles apparently. So what we can do is we can increase the number of neurons, hidden layer neurons, and see. See, now it has a bigger workforce, and now it could separate it very neatly. Do you see the importance of this number of hidden layer neurons now? Because each represents a straight line, and using those straight lines, it can create this kind of boundary. As one last thing, if you could take something like this, right? This is a very complex class, right? So classification. So it needs a very complex pattern to separate these two classes. Can this ReLU-based neural network perform, right? Let's run this. It can't learn this, right? So it attempts to learn, but now you can see that ReLU is much powerful compared to other activation functions, but still it is not capable of doing. Now what can we do? We can increase the number of hidden layers. Now we have only one hidden layer here. Now we increase the number of hidden layers to, let's say, 3, right? And I'm going to have a sort of a balance like this, 4 from this, and middle one has 5, right? can change. I don't have a special reason for having this configuration, right? I just had 3 in-layer inputs. What is this? This is what we call deep learning, right? You increase the number of hidden layers. This is the deep learning architecture. Now see whether this deep learning architecture can find a boundary. We are using ReLU here, right? Let's run this. You can see it gradually constructs some interesting patterns here, right? Now it has completed up to this point, right? With more time, with more iterations, it perhaps construct something, right? We don't know. Perhaps. Now it has classified, it has this section actually. It has this section to complete. So far, it's not doing well. Right? 1000. So if we let it run for substantial time, or else, if we increase this by a little bit more, so actually I constructed a boundary using this configuration. You can try it out. I see. Now it's almost done, right? Only this part is missing. So can it generate that part also? It will generate, right? It will generate. Only thing is it requires some time. Now see, the boundary is almost done, right? Almost done. So this is a simulator, right? Nothing else but a simulator. So this is not a neural network which helps you to submit some answers from one end and get an answer later on, but it shows you how this neural network functions and its capabilities. So play around with this. It's a TensorFlow playground. I did not know about this at the time of doing your lecture, right? So I did not know. But when I was searching for information for some other work, I found this out, and so I'm presenting it to you now. So you can play with that and do experiments, right? If I create it according to this architecture, what's going to happen? If I do create it according to this architecture, what's going to happen? So you can do experiments and try to learn. Let's move on. Here it says, suppose the following data set is given and we use an artificial neuron to learn its pattern. Explain how learning happens in this artificial neuron, right? Only an explanation, but it doesn't mean that I'm going to ask the same question from you, right? So I can even ask other questions. How learning happens. Now here you have, how many inputs do you have? Like you have 7 data points, right? You have 7 data points. And you have 3 inputs, right? Three input values, right? So 0, 0, 0, 0, 0, 1. So you have 3 inputs, right? You have 3 inputs, 0, 0, 0, 0, 0, 1, right? 0, 1, 0. So likewise, you have can take inputs, right? And that is given to the neuron. The output 0 or 1, right? Y could be either 0 or 1. So you have 1 output, 3 inputs, right? So now you have to explain, right? So you expose this to Adeline architecture, right? So if you have studied Adeline, well, you must understand. So according to Adeline, you provide this set of data into the system, and it generates the overall error, right? Using mean square or something, or sum of squared error or something. And according to that error, it makes an adjustment to the W, right? So adjustment to the W. You don't have to explain the entire mathematics behind the Adeline learning process, but you have to show an understanding of that learning process, right? So you must explain using some examples, for example, something like that. why do we need neural network architectures instead of single neuron architectures like Adeline when solving real world problems? Now you just saw that using that simulator, right? That is the reason why you need neural networks, but not single neurons. Okay. You can understand this question very well by looking at the TensorFlow playground. Final question is from rule-based systems, expert systems, and fuzzy logic systems. Describe forward chaining and backward chaining in expert systems. Right? I explained this. Forward chaining means okay. Forward chaining means now you have some facts, right? So you have fact 1, fact 2. Right? From these two facts, you derive a new fact. Right? So a new observation. Right? So, and from these facts, you make another fact. Okay? So forward chaining means you are predicting what is going to happen. Right? What is going to happen. Right? From these two facts, you predict this one. From these two facts, 2 facts, so 3 facts, so whatever, right? So it can not only 2 always. So you predict these 2, right? And from these 2, you predict this one. So forward chain, right? So let's say I passed my master's course today, and I faced a job interview successfully, and because of that I am going to get a better job, and also I built up my some other competencies, and because of that I am going to get a foreign employment. So like forward, right? Forward chain. Backward chaining is the reverse, right? I am suffering from asthma because of, could be these 2 reasons, and these 2 happen because of this, right? It's like a root cause analysis, right? Root cause. So you see an observation now, and you are finding out what could be the root causes for this observation. A doctor, while treating the immediate condition of the patient, tries to observe why the particular observation has occurred, right? Now, what is the reason for the current economic crisis of Sri Lanka? It's a complex problem, but can we move back and find out what could be the root cause reasons for it, right? This one is forward chaining, means finding certain facts, which certain observation that you have right now. Using those observations, you see what is going to happen in the future, right? That's the difference between forward chaining and backward chaining. So in expert systems, you have rules, right? You have rules. For example, if F1 and F2, then it's going to happen something like this. If F3 and F4, then it's going to happen something like this. If this one and this one, then this is going to happen. So it's like those rules are going to tell you what is going to happen in the future. So here it's the backward chaining, means you have some observation here, and from that you find out what facts have contributed to this, and for each fact, what other facts have contributed. So you go back. Forward chaining and backward chaining. Next thing is, what is the relationship between fuzzy variable and membership function? Right? We learned that, for example, temperature is a fuzzy variable. Right? It's a variable that can contain some fuzzy elements, right? Or fuzzy values. For example, for the temperature variable, you can have fuzzy values like cool, cold, cold, cool, warm, hot, right? Cold, cool, warm, hot. What is the what's the exact measure of cold? What is the exact measure of cool? What is the exact measure of warm? What is the exact measure of hot? There's nothing like that, right? There's no particular element to say that it is cold. What you have is a particular temperature value which could be cold, which could be cool, right? Which could be cool, which could be warm at the same time. So each temperature has a sort of membership, right? Each temperature has a kind of membership in those different fuzzy values. For example, 20 centigrade could be a member of the cool value, cool class, as well as the warm class to some degree, right? So 20 could be to a lower degree, it could be cool, to a higher degree, it could be warm. Right? So membership function defines that membership or the degree of belongingness for a particular temperature value, for example, right? So for a particular crisp temperature value, crisp value is the exact value. Fuzzy value means that big value, right? So for a crisp temperature value like 25 centigrade, you can define a membership of that to different fuzzy classes. That is what done by membership functions. Consider the following membership functions of the values cold, warm, and hot. Right? So you must read this as the membership of y in the membership of y in the cool class or cold class. Membership of y, mu is the membership, right? So membership of y in the warm class. Membership of y in the hot class. So that is how you should read it. And this is how it is defined. I have taught you how to construct this, right? How do you construct this? Okay. So you can have this is membership, right? So this you have membership, and the highest membership is 1. The lowest is 0. So any membership should be between 0 and 1, right? So the temperature values are like the maximum is 35, right? So I can say, I can put 10 here, right? I can put 10 here, and this 0 belongs to the y-axis, right? So I cut this. 10 is for the x-axis. So 10, 20, 30, 40, let's say, right? Now I define my scale by looking at these numbers, right? 1 when y is less than or equal 10. So this is y value, right? This is y value, and this is a membership. When y value is less than or equal 10, right? I'm talking about the cold class now, right? So I'm going to draw the membership function of the cold class. When y value is less than or equal 10, it is 1, right? So I can now say, take a look at color. Okay. Less than 10. 10 is here. So less than 10, it's going to be 1. Between 10 and 20, right? So when y is greater than 10 and less than or equal 20, it is going to be defined by this one. So I taught you how to do that now. So if y equal 10, right? If y equal 10, what is the membership value? 2 minus 10 divided by 10, right? 10 divided by 10 is 1. 2 minus 1 is 1. So when y equal 10, it is 1. Membership is 1. When y equal 20, what is the value? Right? It is 2 minus 20 divided by 10. Right? What I did was I substituted y here, right? So when y equal 20, it is 2 minus 20 divided by 10. So what is that? 2, right? 2 minus 2 is 0. So I can say when x is slightly above 10, it is 1, right? So slightly above 10, it's 1 here. When it is 20, when it's 20, it is 0. So it's 0 here. So now I can connect the 2. I can connect the 2. From there onwards, it's going to be fixed at 0. Fixed at 0. So this is the membership function of the cold class. It's cold. Right? How about the warm class? For the warm class, let me take a different color for that. Right? Blue. This one. Let's take this color, right? Same thing. So when y between 10 and 20, right? So what I can do is y equal 10 and y, it's a fancy one, right? For 20. So y equal 10. 10 divided by 10 is 1. 1 minus 1 is 0, right? So it is 0. When y equal 20, 20 divided by 10 is 2. 2 minus 1 is 1. It is 1, right? So when it's 10, it's 0, right? When it is 20, it is 1. Okay, so I can now connect the two here. For this one, between 20 and 25, it is 1, right? So where's 25? Let's define 25 to be here, right? So between that, it's going to be flat. So there's an announcement going outside, so don't. How about this one? 25 and 35. So y equal 25 means 25 divided by 10 is 2.5. 3.5 minus 2.5 is 1. Y equal 35. 35 divided by 10 is 3.5. 3.5 minus 3.5 is 0. Right? So it's 25, it's 1. 35 is here. So 35 is 0. Right? So you connect these two. My straight line is upset, but take it correctly. Right. So this is the warm class. Okay. We'll take another color here for the last one. Right. So when y equal 25, what's that? Okay. So y equals 25, right? Y equal 25. It's 25 divided by 10, 2.5. 2.5 minus 2.5, it's 0, right? Y equal 35. 35 divided by 10 is 3.5. 3.5 minus 2.5, it's 1, right? So y equal 25, it's 0. Y equal 35, it's 1, right? So I can connect these two. When it's greater than 35, it's 1, right? So it's going to be like this. Now remember, we learned that the shape of the membership function can be like the basic shapes are singleton, triangular, trapezoidal, right? So Gaussian. So there are different shapes. In my slide set, you have those things. This is what we call trapezoidal membership function, the shape, right? Trapezoidal shape. So because the tip of the mountain is flat. Now draw the above membership functions on a single graph. So that's what we have done here, right? So drawing them on a single graph. Which of the function above, if any, is not a valid membership function? Justify your answer. So if I have now in this case, is there a non-valid membership function? I have if any, right? There's no such invalid membership function here. What is the reason? Where it can go wrong is that the membership can be above 1 or below 0, right? For example, a particular membership function is moving like this after this point, right? Not instead of going down, it moves up. That's not a valid membership function. It has an error. Or else it talks about a membership which is below 0, right? Somewhere here. Then it's not a valid membership function, right? So, but in this case, all are well in the range of 0 and 1, and they look very well defined. So it follows the straight shape. So it's valid membership function, right? But there's a chance that I can make some tweaks and make it non-valid membership functions as well. Yeah, an additional question that I might ask is, for example, a given day which is it has 32 centigrade, right? So 32 centigrade in temperature. I will ask you whether is that day warm or hot, right? Which class, which category, what is the outcome? What should be the outcome? Then you should show me that, okay, 32 has about 0.8 membership in the hot class, at the same time about 0.2 membership in 2.3 membership in the warm class as well, right? So that fuzziness and membership you must explain using it, right? So basically I covered this paper, and I covered the essential concepts of the essential topics that we covered in this module as well. Do you have anything addition to ask? Now it's 10:17. I have taken 7 minutes extra. Do you have anything else to ask? Okay, study well, right? Go through the recordings that we that I have uploaded. I heard that 14th recording is missing. Let me check on that. I thought I uploaded, but I have to check it, right? And go through those recordings. Study well. When you are answering, answer to the point. Use nice handwriting. Right? Be very careful about that. Use right handwriting. Don't. I mean, be careful about your handwriting, because sometimes it's really hard to read your answers. Okay, and also answer to the point. It is very important that you answer to the point, mentioning each and every important fact. Right? Important fact. Don't write irrelevant facts. Don't write lengthy answers full of unnecessary information. Write only the necessary answers, but make it very concise, precise, and clear. Okay, and also make sure that you write your student numbers and those things. Some people forget to write those things as well. Okay, and read your questions properly. Study well, and come to the exam well prepared. You can go to the question is, it can show some example states in the state space for n by n board example for n queens, right? Pins queens. You can't show n by n. You can say you have to put a value to n. If it is 8, it's 8 by 8, then 8 queens. If it is 4, 4 by 4, then 4 queens. Now in my slide set, there is a video, right? In that video, that state representation is well explained, right? So watch that video. It's a short video. You can understand. Okay. Right. Shall we wind up? Right. So again, there are techniques that we did not discuss in the class. Some of the techniques that we did not discuss in the class, we will cover under machine learning topic. I don't know who is going to do that subject, but whoever does that will cover those things. Particularly machine learning techniques will be covered inside that. Techniques like swarm intelligence are useful, but I did not pick up that as a part of this module. Mainly because I wanted to give you the basic understanding, the fundamental foundational level understanding of this intelligence, state representation, and those kind of things I wanted to give as a part of this discussion. So I hope I have covered the essentials like neural network, the fuzzy logic, rule-based systems, and genetic algorithms, and search, right? So those are the basic essential components of artificial intelligence. So you can build upon those things, because state representation, optimization, and those two, right? Those two are basically almost everything. Right. That's it from my side, right? Then I will wind up for today. I'll see you at the date of the exam, the day of the exam, and take care and good luck with your study. Good luck with your exam. Right? Good night.